Welcome back, everyone. If you've been following along, you might remember that in a previous video, we worked through detailed solutions for the first 4 problems in Griffiths Introduction to Quantum Mechanics. In this video, we're diving into problem 2.5, and we'll break it down step by step to make sure you fully understand the concepts and calculations involved. Let's get started. In this section, we'll tackle problem 2.5, part A. The objective is to normalize the initial wave function of a particle confined to an infinite square well, which is described as an even combination of the first 2 stationary states. We'll take advantage of the orthonormality property of the stationary states to determine the normalization constant A. Once normalized at time equals 0, the wave function remains normalized over time, a concept we'll revisit in part B of this problem. Let's dive in. The problem states that the initial wave function of the particle is as follows. For a particle in an infinite square well, the stationary states psi n of x are given by the following equation. Here, a is the width of the well, and n represents the quantum number associated with the state. Substituting n equals 1 and n equals 2, we get the corresponding stationary states. Now substituting these expressions into psi of x at t equals 0 and factoring out square root of 2 over a, we arrive at the following equation. At this point, our goal is to normalize the wave function by determining the value of the constant a. Normalization ensures that the total probability of locating the particle anywhere within the well is equal to 1. Mathematically, this requirement is expressed as follows. We start by recognizing that the square of psi is simply the product of psi with its complex conjugate. Next, we substitute the initial wave function from the previous step into this integral. Since the wave function at time equals 0 is real, its conjugate is identical to itself. Expanding the square, we get 3 terms inside the integral. Let's compute each of them step by step. For the first integral, we use the trigonometric identity to split the integral. After evaluating at the boundaries, the result of the integral is simply a over 2. Now let's move to the third term, which comes from squaring psi 2 of x. Since the process is identical to the first term, we can use the same method to resolve the integral, and the result is also a over 2. For the middle term, we use the product to sum identity to rewrite the product of sine functions as a sum of cosines. Both terms here evaluate to 0 because cosine functions, when integrated over a full period, result in 0. Finally, substituting all the results back into the normalization equation, we find that the normalization constant a is 1 over the square root of 2. Now let's move on to part B of problem 2.5. In this part, we aim to determine the general solution, psi of x and t, and the probability density, which is the square of the absolute value of psi, based on the given initial wave function. We'll also express the result as a sinusoidal function of time, as shown in example 2.1. The problem simplifies our work by defining omega as pi squared times h bar divided by 2ma squared. We already calculated the normalization constant a in part A. Substituting this value into the initial wave function gives the following expression for the initial wave function. The general solution for a particle in an infinite square well is a sum of stationary states, with each term multiplied by a time-dependent phase factor. Here, b sub n are constants, psi sub n of x are the stationary states, and E sub n represents the energy of the nth state. The problem defines omega as pi squared h bar divided by 2ma squared. So we can rewrite the energy as follows. Substituting this into the phase factor, the wave function becomes the following. At time t equals 0, the time-dependent phase factors become 1, so the general solution simplifies to the following sum. By comparing the coefficients of this expression with the initial wave function we were given, we observe that b sub 1 and b sub 2 are both 1 over the square root of 2, and for n greater than or equal to 3, all b sub n constants must be 0. This is because the initial wave function only involves the first 2 stationary states. Now, we return to the general solution, psi of x and t. Substituting the constants we just determined, we find that all terms for n greater than or equal to 3 vanish. Substituting the constants for the first two terms, the general solution becomes as follows. Next, we compute the complex conjugate of psi. This simply flips the sign of the imaginary terms in the exponentials. Finally, we calculate the probability density, which is the square of the absolute value of psi, the product of psi and its complex conjugate. This final expression represents the probability density as a sinusoidal function of time as required by the problem. In part C, we'll calculate the expectation value of the position, which represents the average position of the particle within the infinite square well for the given initial wave function. We will observe that this value oscillates over time, and our objective is to determine the angular frequency and amplitude of this oscillation. We start with the expectation formula for the expectation value of the position. Mathematically, in this case, it doesn't matter where we place the x. However, for other observables, the placement of the variable can be crucial. For simplicity, we replace psi multiplied by the complex conjugate of psi with the absolute value of psi squared, which is a common substitution in quantum mechanical integrals. This simplifies our task, as we already calculated psi squared in part B. Now, we substitute this expression into the integral for the expectation value of the position, and the result can be split into 3 separate integrals. We now solve these integrals step by step. Let's start with the first integral. To simplify this integral, we'll use the trigonometric identity for the sine squared term. Now we've broken the integral into 2 separate terms. The first integral is straightforward to calculate, and its result is simply a squared over 2. For the second integral, we'll use integration by parts. After substituting into the integration by parts formula, we obtain the following expression. We now evaluate the first term at the boundaries, and we see that it vanishes. The second term also evaluates to 0 because the sine function completes a full oscillation over the interval from 0 to a. Therefore, the entire second integral equals 0. Now, putting everything together, the solution for the first integral is a squared over 4. The third integral is very similar to the first one. If we apply the same approach, using the trigonometric identity and simplifying the expression, we can see that the result will be the same as a squared over 4. For the middle term, we use the product to sum identity. This identity allows us to convert the product of 2 trigonometric functions into a sum of simpler terms, which is easier to integrate. After evaluating at the boundaries, the result of the integral is as follows. Now, after evaluating each integral, we combine the results to express the expectation value of position as follows. We can see that the expectation value of x oscillates over time, exhibiting a specific amplitude and angular frequency. We know that the position of the particle in an infinite square well is always confined within the well, meaning the expectation value of x must lie between 0 and a, where a is the width of the well. This implies that the amplitude of the oscillation must be less than a over 2. Our result aligns with this constraint, confirming that our amplitude is valid, and thankfully, we don't go to jail. Let's move on to part D of problem 2.5, where we need to compute the expectation value of momentum. We're supposed to tackle this quickly, as Griffiths humorously suggests, using a line inspired by Peter Lorre from The Maltese Falcon. So let's dive straight into it. A quick method to calculate the expectation value of momentum is by applying Ehrenfest's theorem. This involves taking the time derivative of the expectation value of position and then multiplying the result by the mass, m. We simply substitute the expectation value of position, which we calculated in part C, and take its derivative with respect to time. And this is the final result. As we can see, the expectation value of p also oscillates over time. Now let's move on to part E of problem 2.5. In this part, we are asked what values we might get if we measured the energy of the particle, and what the probabilities of getting each of those values would be. From part A, We already calculated the normalization constant, which is 1 over the square root of 2. So, we know the general wave function of the system at time t is as follows. Here, E1 and E2 are the energy levels of the first two stationary states. Since the coefficients in front of both terms are identical, we can conclude that the probability of measuring either of these energy levels is the same, which is 1/2 for each. Now, to calculate the expectation value of the Hamiltonian, we use the following formula. Substituting the probabilities and energy levels, we get the result for the expectation value of the Hamiltonian. And with that, we've completed all parts of problem 2.5. Before we wrap up this video, I'd like to leave you with something to enhance your understanding further. Take some time to visualize how the first two stationary states in the infinite square well evolve over time and compare those to the specific general solution we solved in problem 2.5. This contrast between stationary states and the general solution is fascinating, and visualizing it can help deepen your understanding of how quantum states evolve. So, let's dive into those visualizations and explore this further. And that wraps up the detailed solutions for problem 2.5 from Griffiths Introduction to Quantum Mechanics. If you enjoyed this video or found it useful, please give it a thumbs up and consider subscribing to the channel. Thank you for watching, and see you in the next one.